Here I'm going to go over wavelength, frequency, and energy calculations utilizing Planck's constant E equals h times v in this DeBacco University video. So as we can see in this image, the equation, not all that difficult. Energy equals Planck's constant times frequency. What could be so hard about that? We need to have a little bit of a deeper understanding to be able to utilize this, while it may seem quite simple. So first off, we have those equation variables. E, again, stands for energy, the amount of energy carried by a photon or wave. It's typically measured in joules. Frequency, represented by this V, represents the number of wave cycles passing at a point per second. It's measured in Hertz, which is equivalent to cycles per second. Wavelength, by lambda, represents the distance between two corresponding points on consecutive waves, typically measured in meters or nanometers. Planck's constant, 6.62 times 10 to the negative 34th joules per second, fundamental constant in quantum mechanics. And then the speed of light, 3.00 times 10 to the 8 meters per second, the speed at which electromagnetic radiation propagates in basically a vacuum. And we typically round that number, and the one in bold here is the one we typically use. Again, the relation here hasn't really changed. E equals hv equals also hc over wavelength, or lambda here. So again, here is kind of your relation of all those variables, and here's your explanation of those. But because we deal with a lot of these scientific notation numbers, these big numbers might seem a little confusing. So first off, as I said, meters and nanometers. The conversion factor is 1 meter equals 10 to the 9th nanometers. So if you're giving something in nanometers, you're going to need to be able to convert that into meters to be able to utilize this equation. So again, that's the first part that can be a little confusing there. So for example, if you're given 700 nanometers, how do you convert that to meters? Well, n equals the nano, it's 10 to the 9th. So we take that 700 nanometers, we convert it to 1 meter is the same as 1 times 10 to the 9th nanometers. This allows us to cancel out our nanometers. 700 times 1 divided by 1 times 10 to the 9th essentially equals 7.00 times 10 to the negative 7th meters. So that's the first part where students can get tripped up a little bit. Then we get Planck's constant kind of equation here. The equation directly relates to the energy of a photon and its frequency. The energy is directly proportional to frequency. So calculate the energy of a photon of light with frequency 4 times 10 to the 14th Hertz. Here's our equation. We substitute values. Essentially, we get our constant here, which is Planck's constant, 6.63 times 10 to the negative 34. We times that by the 4 times 10 to the 14th. And because we're limited to 3 significant figures, the answer would be 2.65 times 10 to the negative 19th. Again, a little confusing because we have to deal with these exponents and the scientific notation, and being comfortable with inputting that properly into your calculator can be another stumbling point for this relatively simple equation. So the relationship between speed of light, frequency, and wavelength, we can see that correlated right here. C equals lambda v. This equation links the speed of light, wavelength, and the frequency. Wavelength and frequency are inversely proportional for a given speed of light. It means as one is increasing, think of a seesaw, the other one will be decreasing. To give you another example here, the frequency of violent light with a wavelength 400 nanometers. You can go through the process here. We can see that the speed of light is constant. I provide you with the wavelength. Nanometers, we have to then convert that to meters. Simply plug that into the equation, and we should get 7.50 times 10 to the 14th Hertz. And then lastly, combining the two equations, where it might get a little next step or a little more confusing. This equation essentially combines the previous two, allowing energy to be directly calculated from wavelength. Energy is inversely proportional to wavelength. And this visual might help you kind of remember it here. We're looking at the triangle, again, dividing, multiplying, or dividing for the same equation here. Again, working with these a little bit might seem initially that the equation is quite simple, and it is, but understanding where these terms are coming from, how to relate them, and also how to input them into your calculator is typically where I find most students get tripped up. But hopefully this video was helpful to help explain some of this. You can go back and review it, work through some problems, and hopefully the working with the equation will seem as easy as the equation did on the title slide.